In this lesson, we'll look at the end behavior of polynomial functions, and we'll start with a little warm-up exercise just to remind ourselves what end behavior is all about. So take a look at the graph on the right here. We're going to state the end behavior for this polynomial function. So how do we do that? Well, we need to state two things. First, we need to look at what happens to the y values as x approaches infinity. Now, as x approaches infinity, well, that means that we're moving to the far right on our graph here. And as we move to the far right, what's happening to our y values? Well, they're becoming bigger and bigger and bigger negative values. They're becoming more and more negative, so we could say that y is approaching negative infinity. But we also need to look at what happens to those y values as x approaches negative infinity. So that is as we move to the far left on our graph. And as we move that way, notice that our y values are becoming bigger and bigger and bigger positive values. So we could say y is approaching infinity. Now, a question, something to think about. If we were just given the equation of a polynomial function, would that be enough to determine the function's end behavior? Turns out it actually is. And we just need to know two pieces of information about the function. One of those pieces of information is the degree. Now remember, the degree of a polynomial function is the highest exponent on the variable, which in our example here is x. So this is a degree 3 polynomial function here. And we also need to know the leading coefficient. Now the leading coefficient is just the coefficient of the highest power of x. So in our example here, that is 4. So how do we use these two pieces of information to figure out the end behavior for a polynomial function? Well, let's take a look at a specific polynomial function. Consider the equation of the polynomial function that we have here, f of x equals 2x cubed plus 4x squared plus 5x plus 8. Let's think about what happens to each term of this function as x gets bigger and bigger and bigger. That is, as x approaches infinity. And we'll start with the last term there, the 8. What happens to that term, 8, as x gets bigger and bigger and bigger? Well, nothing happens because it's just 8. There is no x with it. It's just a constant. So it doesn't change as x gets bigger and bigger and bigger. But let's now look at this term here, 5x. What happens to that term as x gets bigger and bigger and bigger? Well, as x approaches infinity, 5 times x will also approach infinity. It will become a larger and larger and larger positive value. So that term gets bigger. But look at this term, 4x squared. What happens to that as x gets bigger and bigger and bigger? That is, as it approaches infinity, it gets a lot bigger because we're squaring x here. And when you take those x values that are getting larger and larger and larger, and you square them, we get really huge values. So this term gets a lot bigger, a lot quicker than the 5x term because of the squaring. And for the same reason, our 2x cubed term here gets really big, really fast compared to the other terms because now we're cubing x. And as you can imagine, if you start putting in larger and larger values for x and now you cube them, the results you get are massive, especially when compared to our other terms here. So it turns out that as x approaches infinity, the highest power of x, which is this 2x cubed term here, quickly overpowers the other terms, that is, in terms of their size, making them seem insignificant. So once again, as x gets larger and larger and larger, this term here gets so big compared to the other terms that it makes the other terms look insignificant. So if we want to figure out what our function here does as x approaches infinity, all we really need to think about is what happens to the highest power of x as x approaches infinity. And what's that highest power of x here? It's this 2x cubed term. So let's think about what happens to that term as x gets bigger and bigger and bigger. Well, what does happen to 2x cubed as x approaches infinity? Well, you imagine subbing in bigger and bigger values for x, and when you cube them and then multiply by 2, the results that you're going to get are also going to be getting bigger and bigger and bigger, and they're going to be positive as x approaches infinity. So we could say that as x approaches infinity, 2x cubed also approaches infinity. We can use the same approach to determine what happens to our function as x approaches negative infinity. Just imagine substituting really large negative values in for x here. As those values become more and more negative, what happens to 2x cubed? Well, it also becomes more and more negative because you're cubing negative values, which give gives you negative results, and multiplying by 2 doesn't change the fact that those results are negative. So as x becomes more and more negative, 2x cubed also gets more and more negative. So we could say as x approaches negative infinity, 2x cubed approaches negative infinity. This is very much like what you see with the graph of y equals x cubed. On the right side, the y values are going up to infinity. On the left side, they're going down toward negative infinity. So we know what happens for y equals 2x cubed, the ends of that particular function. So we can now use this information to look at what happens to the ends of our function f at x. And it is exactly the same. Whatever's happening to the ends of y equals 2x cubed is what is going to happen to the ends of our function f at x right here. So what is that? Well, as x approaches infinity, our function here, f at x, is also going to approach infinity because that's what's happening to 2x cubed, that biggest power of x. Similarly, as x approaches negative infinity, our function f at x will approach negative infinity because that's what 2x cubed is doing. Okay, so it's all about that highest power of x. Now, a warning, we've been saying things like, once x gets large enough, once we talk about really big positive or negative x values, these terms here don't matter. That is only true because we're talking about large x values, positive or negative. If we're talking about x values that aren't large, these terms have a significant impact on the value of our function. Like if you're subbing in 1 or 2 or 5 or negative 10 or something like that, these three terms here do have a big impact on the value of this function. It's just when we start using really big positive or negative x values that these terms don't really seem to matter because that 2x cubed kind of takes over and it overpowers everything in terms of size. So some quick questions for discussion. How would this change if our function was g at x equals negative 2x cubed plus 4x squared plus 5x plus 8? Would the end behavior be the same? Well, no, it wouldn't actually, because now we still have everything the same here, except there's a negative 2 with x cubed instead of a positive 2 here. So what happens to the end behavior? Well, now as x gets bigger and bigger positively, x cubed gets bigger and bigger positively as well. But when we multiply by negative 2, those values actually become now bigger and bigger negatives. So as x approaches infinity, negative 2x cubed approaches negative infinity. So this whole function approaches negative infinity, which is the opposite of what we have for f at x. And for the same reason, as x approaches negative infinity, imagine these x values becoming bigger and bigger negative values. When you cube them, now you're going to get negative results, which when you multiply by negative 2 will give you positive results. So as x becomes more and more negative here, as it approaches negative infinity, negative 2x cubed actually approaches positive infinity, which means this function approaches positive infinity, which is again the opposite of this. So notice that because we have a function that is degree 3 here, the ends of the function go in the opposite direction. If we had a positive leading coefficient, our positive end here, as x approaches positive infinity, went up to infinity. And as we approach negative infinity for x, the function went to negative infinity. But the opposite would happen if we had a negative leading coefficient. All right, one other question here. Would the end behavior for the function h at x equals 2x to the 4 plus all that other stuff be the same as our function here? Well, actually, no, it wouldn't, because now we have x to the 4. And you can imagine subbing in bigger and bigger values for x. Now, whether those values are getting more and more positive or more negative, when you put them to the power of 4, the result you get is going to be positive. So as x approaches positive infinity or negative infinity, when you put that to the power of 4, those values, you get a positive result, and multiply it by 2, and you're still getting positive results. So in summary, what happens, because this is an even number, this exponent here, as x approaches infinity or as x approaches negative infinity, this 2x to the 4 term is going to approach positive infinity, which means this entire function will approach positive infinity. So the ends of this function go in the same direction. In this case, they both go up to positive infinity because we have a positive leading coefficient. If this was a negative 2, well, it kind of flips everything, right? Now those positive results you get from x to the power of 4, they get multiplied by negative 2. So your n's are going to approach negative infinity. All right. Let's move on, and we'll finish up here with just some quick examples. And we'll state the end behavior. So we have our first function, which is f at x equals negative 6x to the 4 plus 3x cubed minus x plus 2. And we'll start by stating the important information here, which is the degree. It's a degree 4 polynomial function, and we'll note that's an even number. Okay, that's going to come in handy when we go to think about the end behavior. And the leading coefficient, which is negative 6. Now that's a negative leading coefficient. It's really the sign of that number that matters here. So what is the end behavior? Well, as x approaches infinity, what happens to this function? We need to look at this negative 6x to the 4. And because this is a 4, we're going to have the ends going in the same direction. Now, the big question is it up or down? Well, we have a negative leading coefficient, which means as x approaches infinity, negative 6x to the 4 is going to approach negative infinity here. Which means that f at x will approach negative infinity as well. And the same thing's going to happen when x approaches negative infinity because we have an even number here for this exponent. It's a degree 4 polynomial function. As x approaches negative infinity, these results for x to the 4 approach positive infinity because we have a 4 for the exponent. But then when we multiply them by negative 6, those results become negative. So we're going to approach negative infinity for this first term, which means the whole function f at x will approach negative infinity. And one last example here. What is our degree for this function? Highest exponent on x is a 3. Now that's odd, so that tells us right away the ends are going to be pointing in opposite directions. We just need to determine which end points up and which one points down. And that will be determined from the leading coefficient, which is negative 5. Right? Now, if our leading coefficient was positive, then as x approaches infinity, this function would approach infinity. But because it's a negative 5, that's not going to happen. It's going to be the opposite. As x approaches infinity, our function here, y, is going to approach negative infinity. And then as x approaches negative infinity, our function will approach infinity. Okay? And if you want to think about why that is, just imagine subbing in bigger and bigger negative x values here. Cube them, you still get negatives. Multiply by negative 5. Now you're getting bigger and bigger positives. And this term kind of takes over the whole function as x gets more and more negative as it approaches negative infinity. So we start to approach positive infinity. Okay, so that is end behavior for polynomial functions and how you can figure out the end behavior by just looking at the equation of the function.